Hello? Okay, so let's get started. Hope you had a nice lunch and a break and discussion. So we have a lot of exciting talks in the afternoon, and we'll start with Gilad Shainer from NVIDIA. The previous one is Mellanox. Of course, many of you in the community know Gilad. I don't have to read everything. He's very well known, but he serves as the Vice President of Networking at NVIDIA, and he's the chairman of the HPC Advisory Council, and he has done a lot of work. And he, especially these days, like he's leading the UCX consortium. Okay, so with this, let's welcome Gilad.
Thank you, DK. Yeah, I think the mic is on, right? Yeah. So I will talk about NVIDIA InfiniBand platform in more details. But before that, kind of give you a little bit of an overview of why we're doing what we're doing. Please feel free, as in previous talk, if you have any questions or comments, just to raise your hands and we can do it immediately. No need to wait for the end. So AI has become the new tool for science. Same as GPU enabled increased computing capabilities. The combinations of AI and simulations enable to enhance science in multiple domains. I wanted to say that but almost every supercomputer that is being built, it's actually also an AI supercomputer. Now, AI is going to be used by essentially every company. There are going to be many more users that need access to AI, using AI, many more companies that need access or using AI. And that means that for supercomputing sites, that's a great opportunity to have more users to serve, to support more companies, essentially, more users, more applications. On the other end, it does bring a new challenge, because supporting more users and more companies and different kind of users means that you need to bring infrastructure services. In order to enable supercomputing as a service to more users, we need to start looking on security and isolation. We need to start managing I/O access. So we actually need to bring tools that exist today on cloud infrastructures into supercomputing. And that means increase in overhead. That also means that the infrastructure workload will actually become one of the most complicated workloads we deal with. And running that workload on the same compute platform that we have today means that we're going to start losing performance. We're going to start bringing more and more and more overhead. Now, this problem is not just a problem for supercomputing. It's actually a problem that the major cloud providers are dealing with today. Their security demands are growing. They have more users to deal with. Their infrastructure workload is eating more and more from the CPU cores. That means that they're kind of losing capabilities. That's also applied for people that building private clouds. For example, VMware base. Running the hypervisor on the same domain that hosts the applications, that's a security problem. So we actually need to build what we call cloud native supercomputing. An infrastructure that can enable bare metal performance on one side, but on the other side, be able to bring more capabilities around services, more infrastructure services. And we're going to talk how we do that and how we bring that. And obviously, that is not something that just goes to supercomputing. That's something that goes into the major cloud providers, the private cloud. But for supercomputing, there is several services that actually are unique. So the platform that we're talking about, or cloud native supercomputing, it's actually a platform that look into bringing new computing platform. Not just the CPUs or GPUs, but actually the DPUs. The data processing unit is a new compute platform that we bring into the data center or bring into the supercomputer. It's a compute platform that enable different kind of new services that we could not have before. Everything from security services that enables us to move supercomputers into more zero trust supercomputers. Those are services around I/O, around storage, to deal with the jitter issues that file system processes are creating on the clients. Services around MPI, any network computing. Services that will enable us to use non-blocking MPI operations without overhead on the CPU memory. Services around AI and nickel, for example. Services around telemetry, performance isolations, and more. I'm going to show you some examples of what the results of adding or bringing those services are. So the platform that enable, the elements that enable the cloud native supercomputing, it's actually the network infrastructure. So from our perspective, this is the latest InfiniBand platform that we provide today. The Quantum 2 InfiniBand switches, those are switches that runs 400 gigabit per second speed and enable data reductions to be done on the switch itself, on the switch hardware. That covers reduce and non-reduce and barrier and broadcast, for example. The ConnectX, which is the network adapter, 400 gigabit per second PCI Express Gen 5, software-defined device. Bluefield, the data processing unit, which I'm going to talk more about that, what that device is and what that device brings. There is also gateway between InfiniBand and Ethernet to be able to connect the InfiniBand HPC network to an outside Ethernet connectivity, and a full set of management tools for managing, orchestrating, and monitoring the network infrastructure. So if you're going into more details, the Quantum 2 switch, 64 ports of 400 gigabit per second or 128 ports of 200 gigabit per second. It's probably twice the radix or twice the bandwidth per port compared to anything else that exists there from a HPC perspective. 200 nanosecond switch latency. So when we look into RDMA elements, for example, and Mellanox, now NVIDIA, was the one that brought RDMA into Ethernet to be able to bring the effectiveness of moving data to host memory, to Ethernet, the same as we do that on InfiniBand side. The main difference in latencies is the switch. Main differences in latency is the switch. InfiniBand switch is less than half of any fastest Ethernet switch you're going to find out there. And that's a great advantage of InfiniBand being a pure software-defined network and the lowest latency out there. With this radix, you can actually build data centers with more than 1 million endpoints running 400 gigabit per second if you're using Dragonfly topology. Essentially unlimited scale. Adaptive routing, congestion control, and one of the results of that combination is essentially ability to bring more than 95% effective throughput when we're talking about large-scale deployments. Typically on Ethernet, that number goes to 65%. That's why we're seeing increase of InfiniBand in the large AI infrastructure being built by the large cloud providers. ConnectX-7, the network adapter, 400 gigabit per second with PCI Express Gen 5 or Gen 4. There are 32 lanes of PCI Express Gen 5 on the card. Can be used to connect different CPUs to one NIC, for example, for direct connectivity to dual socket CPUs directly. Sub 1 microsecond latency, end-to-end, server to server. Obviously, there are dependencies on different kind of servers, and if you're using an Intel CPU, an AMD CPU, or an ARM CPU, and so forth. But on the fastest system, it's a sub 1 microsecond latency, 330 million messages per second. InfiniBand is the only network, I think, today, still, that combine full transport offload and hardware, native hardware RDMA. That full combination. Moving data directly to host memory, to GP memory, from the storage to GP memory, and so forth. There are dedicated hardware engines for tag matching. And DK showed some results earlier today. And we did introduce with ConnectX 7 a new hardware engines for small message all-to-all operations. To be able to increase all-to-all, small message all-to-all bandwidth by 4 to 5x, compared to running that on a CPU. Now, Bluefield, which is the data processing unit, combines everything in ConnectX 7 with 16 ARM cores, A78, and a full data path accelerator that includes another 16 cores. So there is two programmable engines. One of them is 16 ARM cores, and the second one is a data path accelerator. There is a PCI Express switch to be able to connect to other PCI Express devices, memory interface, DDR5 memory interface, and more engines for infrastructure workloads, specifically for infrastructure workloads. Storage engines that enable to emulate NVMe, to be able to do checksum, to be able to do compression and decompression in hardware. Engines that enable to expose file system services to applications running on top. Then there are security engines around encryption and decryption. I mentioned the compression and decompression before. So essentially, Bluefield can provide, if needed, an encrypted enclave inside of a supercomputer. Now, with the switch, we're building different kind of switch systems. There is the 1U switches that has the 64 ports of 400 or 128 ports of 200. We're also releasing some large switches. The largest one has 2,000 ports, 2K ports of 400 gigabit per second, or 4K ports of 200 gigabit per second. There is a half size of that, and there is also a quarter size of that. So those switches enable to build any sort of topologies, if it's dragonflies or fat trees, different kind of meshes, toruses, and so forth. So let's look into the DPU and actually what we're doing with the DPU and how we use the DPU to build the infrastructure that I mentioned before. So for folks that are not familiar with the DPU, this is how the internal architecture of the DPU looks like. So first it has the entire ConnectX inside, and Bluefield 3 has the entire ConnectX 7 inside. So 400 gigabit per second device, 16 ARM cores, A78. There is data path accelerator that you don't see on this slide here, and the different acceleration engines for storage, for security, for networking. DDR5 memory interface. There is 2 channels of DDR5, and a PCI Express Gen 5 switch that can that has 32 lanes of connectivity, which means you can connect to other devices in the system directly from the DPU. That can be direct connections to GPU, to flash devices, CPUs, and so forth. Bluefield bring the capabilities of essentially building the cloud-native supercomputing. The ability to use the hardware engines, the ARM cores, through the SDK, through the services that we enable for running MPI on the DPU, for running the storage processes on the DPU, for enable adaptive performance isolation, and many other services. There is multiple systems that already multiple sites that already build systems on Bluefield, or actually on Bluefield 2. There are some of them are here. Lone Star 6 attack is now been upgraded from ConnectX 6 actually to Bluefield 2. So they will provide access to a BlueField-2 system. There's a system in Cambridge University. There's actually another one in Durham. There are systems in Los Alamos. Their system is in more places. We're probably going to see a BlueField-2 system in one of the large cloud providers that's going to provide access. And we are bringing BlueField into all of the HPC platforms that we build, including the future DGXs and so forth. From a software perspective, we created an SDK called Docker, which is similar like CUDA for GPUs. There is Docker for DPUs. Docker is a combination of full SDK, so it's software libraries and the development elements, as well as Docker services. Docker services for storage, for security, for networking, for MPI, for Shainer, for Nickel, and so forth. And those services enable applications to actually leverage the DPU for increasing application performance, for improving the infrastructure management on one side, but also enabling to separate between the users and the infrastructure. So sysadmins can completely control the DPU, and through the DPU to completely provision the server, completely provision the data center, and enabling more security and more isolations for the users running on top. So from a installation perspective, that's in a high level how it looks like. BlueField has two I/O connectivities. One of them is the high performance computing one. For example, 400 gigabit per second InfiniBand that can connect to computing infrastructures or storage to form the compute network or to connect to the storage side of things. And there is also a management. There is a 1 gig port that can connect to management entity, to a DPU orchestration, for example. And that can actually be a separate network that only the sysadmin has access to. And through that network, you can load the operating system into the DPU. DPU is essentially running Linux. It's a full computer by itself. So 16 ARM cores that running Ubuntu. So you can load the operating system into the DPU, and then you can load also all the services that you want to offer. For example, to load MPI into the DPU and offload all the MPI services, all the MPI work to the DPU. To move the file system, to enable file system service. So we are moving the file system process that runs on a client from the CPU to run on the DPU itself. And by doing that, we can eliminate the jitter that process creates on a CPU. So application actually getting their storage services from the DPU, from the local device. And then the DPU is the one that actually does all the work, all the management, all the access to the real storage part. The DPU can fully emulate NVMe. So with the DPU, you can actually show an almost unlimited flash capability, NVMe capabilities to the applications running on a server. On the other side, the DPU takes all the local operations, local NVMe operations, and run them on a remote NVMe device. Get the response and then put it back as a local response to the applications. You had a question?
Yeah, so what sort of telemetry can be exported right now from that?
So from a telemetry perspective, the nice part here is that you can get telemetry information from the switches, you can get telemetry information from the network adapters, you can get information from CPUs, GPUs, and stuff like that, right? Now, if you take telemetry information from the server, then you create an overhead by doing that, because the CPU needs to collect that information. The DPU is becoming a focal point for telemetry. So the DPU can actually collect the telemetry information from the server itself without putting an overhead on the CPU and on the DPU. So it can bring you the telemetry information from the switches, telemetry information from itself, and of course telemetry information from the server. Then you can read everything from there. So that's on the telemetry side. And I'm going to mention some of the things that we're kind of looking to use the telemetry information. Yes?
Yeah, I have a question of the storage engine. Sorry. Yeah, about the storage engine, exactly what does that do? Is that just compression, decompression, or does that also provide additional service to that? The
So-
second question, well,
Yeah, let's do
sort of-
one by one.
Okay.
You know, I don't remember what I did yesterday, so it would be hard for me to remember two questions. On the storage side, there's multiple elements. First, checksums is being done on the DPU. Compression, decompression on the DPU. NVMe emulation. So it can emulate itself to be a local NVMe, essentially quote unquote unlimited local NVMe. And also VirtIO. So it can do VirtIO block, VirtIO FS, and so forth, which means is that DPU itself resembles to be the file system, the block storage, for example, to the applications running on that server. So application mounts storage on the DPU locally. The DPU is the one that actually mounts storage on the storage. So all the processes running today, for example, file system process that runs on the client, that actually runs on the DPU. Then the DPU exposes the file system services to the application running on top.
So does the DPU have direct connections to the storage?
Through the network.
So it goes to the host, even though it's not really, the command and execution is done on the DPU, but the actual
Yeah, the
data
DPU is
from
running the
host.
file system processes, for example. Exactly. He's the one that managed that. So through that, you can also control if a user can access a specific storage or cannot access specific storage, for example.
Right.
And then it gives the storage services to the application locally.
Okay. So go through the PCIe, then go through the PCIe. Then
Go through the
directly-
PCIe to the application running on top of the CPU. In any case, you go through the PCIe in that sense, right? In any case. But here, everything is done on the DPU. So you don't have any jitter effects, for example, on the CPU. You can resemble to have unlimited NVMe storage, which effectively you cannot if you're using real local, because there is a limit on the server side. And all the elements of checksums and decompression, stuff like that, that you can reduce the overhead from the CPU.
Okay. Now, what does the UFM here mean? Unified File?
UFM, it's a Unified Fabric Manager. So that's a management, could be appliance or management software that does the orchestration, monitoring, management of the network, quality of service, and so forth. So a few examples. So one thing that we can do with the DPU, as I mentioned, is to move MPI from the host to the DPU. Now, why to move MPI? Why to move MPI? Simple example is non-blocking operations. So non-blocking collective operations were added to the MPI spec, I think it was 10 years ago, exactly 10 years ago, more or less. Something like that, right? But no one actually used them to date. Meaning there were a lot of experiments, and folks took host CPUs and separate some of the cores to run the applications and some cores to run the MPI non-blocking operations. But it's not real separation. Because first you have less cores to run applications, and on the other side, those cores sitting on the same memory complex. So it's actually impact one another. But having a new compute platform as the DPU means that we can move or run non-blocking MPI operations on the DPU. Complete separate compute complex, complete separate memory complex. Now, it's not just the non-blocking collectives, but we can move all collectives. For example, if you're running O2LV, typically you don't just blast data from all the nodes to the network, but using different kind of algorithms. Algorithms that have nodes send data to the neighbors and receiving acknowledgement from the neighbors, and then send data to the neighbors of the neighbors, and so forth. Now, in the cases of loading balancing, my neighbor might be busy. So I'm going to get stuck. Now, if the DPU is the one that's going to get the data, the DPU can release me. So now I can progress. So we're moving all of the multi-process synchronization into the DPU. And why not adding ISEN and iReceive as well? And doing tag matching. And doing tag matching and doing the entire rendezvous protocol. So essentially, you're moving the MPI services or MPI operations to run on the DPU instead of running that on a CPU. And if your application has non-blocking capabilities, for example, and if in average, let's say that application spends in MPI around 30%, 35% from its time, this is the amount of performance boost that we can provide with the DPU. Completely hiding MPI. Zero latency for MPI operations. And this is something that several sites here are actually working on. So Professor DK Pana, for example, showed an example with FFTs. 3-dimensional FFT from San Diego Supercomputing Center, modified the FFT from using blocking all-to-all operations to use non-blocking all-to-all operations, sorry, and achieving more than 25% performance improvement. And it's not the end, because in the current implementation that was done, data was copied to the DPU. And this is unnecessary because the DPU can actually access directly the host memory. So there are several enhancements that are going to come next, and that performance boost actually can become much higher. Georgia Tech and Sandia did an example on MiniMD, actually moving part of MiniMD to run in parallel on the DPU. 20%. Not much of optimizations. We're doing some work right now on several weather codes. So on GSAM from JMA, working with JMA, and there is icon from DKRZ, and the 3D and 4D VAR of UK MAT and IFS, for example, and we're expecting between 20 to 30% performance boost. So in average, DPUs will give us between 1.2 to 1.3x performance improvement for probably every MPI application that exists. That's what the DPU gives. Now we're also working on an MPI compiler that actually can find places for applications that were written using blocking collectives to be able to migrate them to use non-blocking collectives. It's an interesting project. It looks good at this point, and that we actually want to help to migrate a lot of applications. So to move applications that are using blocking collective to use non-blocking collective, and with that be able to leverage the DPU to the max. So MPI workloads 1.2 to 1.3x performance improvement on applications because of the DPU. Now it's not just MPI, but the same things you do with NICO. Moving the data reductions operations, or moving all-to-all operations, and then the DPU can actually run sharp. DPU can enable sharp or move those operations to use the hardware resources that exist. So this is one area. Another area is performance isolation. And what does it mean, performance isolation? I'm good in a few minutes? No. Performance isolation. This is something that is a problem for today infrastructure, today supercomputers as well. When you're hosting multiple applications on the same infrastructure, even that every application or job using different kind of nodes, they're still sharing the same infrastructure, the same network infrastructure, which means that one application can impact another application performance. And you can see the examples here. There's a couple of examples here. This works. So we did a couple of experiments. The first one, we took lamps, just as an example. You can pick any other scientific code if you want to. And we took a supercomputer, and on that supercomputing, we just ran lamps as a single application on that system. And we did it over and over and over again. The x-axis is performance, the y is the number of iterations, and actually we built an histogram of the results. So every time we got pretty much the same result. Makes sense. In the next iteration, we continue to run lamps, but now we also run other jobs on the same system. Here were some IO heavy jobs, and some massive all-to-all operations and so forth. And what happened here is that now we're not getting the same performance with LAMPS, because LAMPS is impacted by other workloads running on the same system, on the same network. So sometimes we get good performance, sometimes we get a little bit less. We have a spread of histogram. We did the same experiment, by the way. So this is done on a supercomputer, simple environment that you can see in multiple places. We did it also on a cloud, on a public cloud infrastructure. And there, the situation was even worse. We lost 2x performance from the get-go. And then it could go to 5x worse. And on the right side, you can see the effect of performance isolation. What does it mean, performance isolation? Performance isolation means the ability of the endpoint, which could be ConnectX or Bluefield, to control injection rates to the network based on destination, based on telemetry data that comes from the switch that indicates many-to-one scenarios, based on round-trip time measurements that are being achieved. There is a sophisticated algorithm that runs on the ConnectX on the DPU that control injection rates per endpoint. And by doing that, making sure that one application will get on one side the best performance it can get, on the other side that it will not impact other workload sharing the same infrastructure. So with doing performance isolation, you can see that you actually get very similar results for LAMPS as it's kind of running by itself when it's actually running on this platform, on a multi-application platform. The same was done with AMG, and if you actually look on different workloads, you're going to see the same thing. Now, what we're doing with the DPU is the ability to optimize that algorithm that enable the performance isolation on every given data center when it's running in production. So the parameters that we enable are based on our testing, on our data center when we're taking extreme conditions. But with the DPU, you can optimize the algorithm that runs on the DPU based on the real workloads that exist, based on the topology of the data center and so forth. There is one more example that I wanted to share with you, and that's something that we're looking to do as well with the DPU. And that kind of relates to telemetry information. Schedulers. Schedulers are working in a very, very simple way. Very simple way for many, many years. If you look on Slurm, Slurm get a list of jobs. On every job, there is a list of how many nodes the job needs. You know, maybe how many CPUs, how many GPUs, essentially how many nodes. And then scheduler look on that, take the job, try to find that number of nodes. If it's lucky, it's actually going to put them together, trying to be some topology or use some topology awareness, and it schedules the job. But there is nothing there that talks about how much I/O that job needs. Not just I/O to the storage, but how much bandwidth this job needs. And one reason is that users don't know. Typically, users have no idea. They know how many nodes they want. Oh, that's running on 60 nodes. How much I/O this job going to consume? I don't know. So this is a good information to actually get. Because if I know how much I/O I need, how much bandwidth I need, I can probably do much better allocation of that job. Or combination of jobs. I probably will not put multiple I/O heavy jobs together on the same area. I might pick some different areas in the data center, the supercomputer, when I'm going to put those jobs that needs more I/O versus less I/O. So we need the ability to actually learn how much bandwidth a job consumes or how much bandwidth a job generates. And the device that can actually do that is the DPU. Because the DPU can create correlation between process ID on one side and how much I/O that job consumed. And since you're not running unique jobs, it's not that every job is unique, but many of the jobs are the same kind of jobs. Then the DPU can give you a good estimation of how much I/O jobs consume or different kind of jobs consume. And you can take that information, pass this to the cluster manager, goes to the scheduler, and actually do much more or better scheduling on the system. There is more things that are being developed on the DPU. So I mentioned MPI, and I show you some results. I mentioned storage, moving the fast system process running on the client to run on the DPU. And with that, eliminate jitter, performance isolation or adaptive performance isolation. And I mentioned something that we start exploring around job schedulers. There are more ideas and more things that are being developed. Happy to work with more people on different kind of collaborations. We provide access to our own system that has DPUs inside, and there are several other systems that I mentioned that will also provide access for doing different kind of developments. So being part of NVIDIA, I think brings great capabilities of actually looking first on the application side of things. And since we're building the 3 computing platforms, GPU, CPU, and the DPU, you can actually move algorithms, move data algorithms, and run them in the right place, in the ultimate place. So we're actually moving things. So we started that by moving data reductions to run on the switch, because when you run data reductions on the switch, you reduce the bandwidth that you need by half. A 400 gigabit per second network with data reduction is equal to 800 gigabit per second network without data reduction. That's a huge impact, huge difference. So moving data reductions to there, moving tag matching, moving the MPI services to the DPU. There are services or elements or issues that the network has, we actually move them to the CPU. For example, dealing with non-continuous data, you probably can do that much easier when you're close to the memory. So there are several things, and with that, I'm a few minutes over. I want to thank you for listening. And if there is any last question, happy to take that. If not, you can do it over the break. Thank you very much.
Any quick questions? Yeah, Matt, please.
So you mentioned about learning I/O bandwidth to your application. Have you made steps towards integrating what that is learned into Slurm or a scheduler of some sort?
Yeah, so we're looking now how to do that. Nice part as being part of NVIDIA is that NVIDIA acquired Bright Computing, so we actually have access to Cluster Manager. So actually bringing that information there is an example, and obviously enable that to other cluster managers. We're working now on building the relationship between the process ID and the I/O, so we can actually form and getting that information in a nice way. And the next step is to work with the job schedulers, for example, Slurm, in order to bring that information to them and start working on that. So we do that in phases. Right now, we're creating the correlations between, on the telemetry base, between the process ID and the DPU, getting that information. The next phase, we'll start working on the schedulers.
One more question. Yeah, go ahead.
Sorry, Gilad. Now coming back to where you upload the I/O storage operations, at least starting from the now for local host, try to do I/O. Does that mean to cross the PCI bus twice?
No, it passes it once.
Then how does the host let the DPU, the storage agent there, to know that you need to do some I/O operation which the device is attached to the host?
You moving the management of file system or storage or whatever through the DPU, right? Now, from the CPU, you move the operations, what you want to do to the DPU. And then the DPU will do the operations and give the results back. So you don't need to go, you don't move the data over PCI Express.
You just move the command.
Just
Data
management.
flow only cross.
Just
Okay.
management.
Thank you.
Alan, yes.
How do you leverage the power of DPUs in existing systems?
How do you?
How do you leverage the power of DPUs? Imagine I have a system with NVIDIA GPUs. I want to optimize the communication. How useful can be DPUs there? Or how can I use them in an existing system?
How do you utilize the DPUs in a system, in a sense? So first for development, if you want to take a DPU and start learning how to use it and how to play with it, DPU, it's a full computer by itself. Meaning, you know, some people consider the DPU as a network device with compute or network device with steroids. Actually, we look on the DPU as a computing platform with networking capabilities. Now, the DPU, if you take it as an open element, meaning you don't put security and isolation and stuff like that, you just SSH to it. It's a full computer running Ubuntu. You can SSH to that, and now you start moving whatever you want to move between the DPU and the host. So that's from a development perspective. What we are doing, and this is, for example, how Professor D.K. Panda started with MVAPIC on the DPU. It's actually, you can SSH to the DPU. You have some processor that runs on the DPU. You move data, metadata from the host to the DPU and have the DPU do whatever you want. Now, the DPU you can copy data to DPUs or actually keep the data on the host memory, and the DPU can actually access it directly. And it doesn't go through the CPU. Now, when it's go to production, in a production environment, you're probably going to close the DPU from being accessed by users because you don't want one user to impact the DPU, which might impact other users. So what's happening there, the DPU still runs as a compute, but you have a different network to access. You don't access that through the server. You can access that through another network. Same as you access other servers through a management network. And once you're there, you have a full computer, so you can put different kind of processes and services, and that's what we do, for example, through Docker. I can give you more information and access to more training about the DPU, and how you can use it.
A DGX system with 8 A100 GPUs. How can the DPU be impactful for me?
So just from a time perspective, maybe we'll take it and cover that on.
We can do some offline discussion so that we'll remain on schedule. So thanks again, Gilad.
Thank you.